I'm not sure how comfortable we are up to now with radicals, with simplifying radicals. But we need to know how to simplify radicals in order to add or subtract them. So I want to add, subtract. Radical expressions. So let's look at an example here. If I have rad 32, and I think we talked about this briefly last time, but let's just make sure we're on the same page here. So I have three radicals here, rad 32, rad 50, rad 2, and I'm trying to subtract these three radicals. If I look at subtracting them the way we have it here, I won't be able to. Why not? Because in a sense here, when you look at them, these are all different radicals. So they're like different things that you're subtracting. They're unlike terms, quote unquote. So you can't combine them. You can't do anything. You just leave it. However, we can try to see if we can break these down. Of course, rad 2 won't be broken down any further. You won't simplify this because it's already simplified. So this is already simplified. I can't do anything further. And remember about simplification in radicals, right? We're trying to find the highest perfect square that divides the number in underneath the radical. So if you look at number one, if you look at rad 32, you have to ask yourself, what two numbers multiply to 32, where one of those numbers is a perfect square? And so the highest perfect square that divides 32 is 16. So I can write this as 16 times 2 because 16 times 2 is 32. And then I can break down the 16 and break down just the 16 because the 16 is the perfect square. And the square root of 16 is 4. So I got 4 rad 2. So instead of writing rad 32, I can write it as 4 square root of 2. And then I can do the same thing for rad 50. Rewrite rad 50 as a product of two numbers. So it's 25 multiplied by 2. So I get the square root of 25 multiplied by the square root of 2. The square root of 25 is 5. So I got 4 rad 2 minus 5 rad 2 minus rad 2. And now look what we have. We got rad 2, rad 2, rad 2. We have like terms now. So these were unlike, and now these are like, or the same. So now we can combine them. 4 rad 2, 5 rad 2 minus 1 rad 2. So you can treat them as objects, as things. So I have 4 things minus 5 things. Or I can write this, this rad 2 here, you can think of this rad 2 as having 1 in front of it. So I have 1 rad 2. So when we have such a thing here, we're really just going to be combining the coefficients. Whenever we combine like terms, right, we're combining the coefficients. So we're leaving the rad 2 the way it is. And we're really just saying, hey, what is 4 minus 5 minus 1? What does that equal? Well, 4 minus 5 is negative 1. Minus 1 is negative 2. So the answer is negative 2 rad 2. So that's how we subtract or combine radical expressions. we break them down so that the thing or the number or the expression inside the radical at the end are all the same. And all those that are the same kind, we combine the coefficients. Okay, so we have to be very comfortable with simplifying, breaking down our radicals, expressions. Okay, so I'll give you another one of these. If I have something like this, 2b square root of 12a cubed b minus a square root of 192 ab cubed. So I have two radicals, and as of right now, they have two different expressions underneath the radicals, so I can't really combine them, right? So these are different or unlike. Different, unlike. So what we try to do is, can we break them down to something that is the same? So that's something we also have to check, right? So the first thing is, what is the cube root, or the square root of 12a cubed b? What does that simplify to? And remember, all we have to do is find the biggest perfect square that divides the expression. So for example, let's look at 12. What multiplies to 12 where one of those numbers, one of those factors is a perfect square. So 12, you can do 2 times 6, but 2 and 6 aren't perfect squares. You realize you can do 4 and 3. 4 times 3, 4 is a perfect square. Okay, now we go to a cubed. I want to break down a cubed. Now a cubed, pardon me, I can rewrite that as something as a perfect square. What divides a cubed? And that is a perfect square. Well, it's the exponent one less than the one that we have now for 3. So for example, a cubed, I can rewrite that as a squared times a. And a squared is a perfect square. So I can break down a cubed as a squared times a. And b, I can just leave it because b is as simple as it gets. I can't break that down any further. So what I'm going to do is I'm going to rewrite all the ones that are perfect squares. I'm going to put them under one perfect square, under one radical. So 4 and a cubed, I'm going to put that under one radical on the left. And on the right, I'm going to put everything that's not a perfect square. So 3ab is not a perfect square. The 3 and the a and the b are not perfect squares. These are not perfect squares. Now, because you're a perfect square, that means that you can find what the square root of it is. So square root of 4a squared is 2a. But I still have this radical 3ab attached to it. So the square root of 12a cubed b reduces or simplifies to 2a rad 3ab. So I can write this now as, and don't forget guys, there's a 2b in front of it from the beginning. All I did was I broke down the radical. So I simplified the radical to 2a, and now I can write this as 2b multiplied by 2a, the square root of 3ab. And then if I combine this here, this becomes 4ab rad 3ab. So far, that's what I have. So I'm going to call this, just to make sure we're on the same page, this is a 1. And I'll call this number 2. So radical number 2, I got the square root of 192 ab cubed. Okay, so now I have to figure out what is a perfect square that divides 192, or I should say, what is the largest perfect square? And if you try, let's see, 12, if you look at it, the highest perfect square is 64. 64 times 3, that gives me 192. So 64 is a perfect square, and it's the largest one. A, I just leave A because A is as simple as it gets. B cubed, I can break down as B squared times B. So this is also a perfect square. What I'm going to do is put in all the perfect squares under one radical. So 64 B squared square root. This becomes 3AB. When I break this down, square root of 64 is 8. Square root of B squared is B. And I get 8B rad 3AB. And I can put that in front here now. I can put this as A multiplied by 8B 3AB. Multiply that out and I get 8AB rad 3AB. You see that? And this here is just, it's just like scratch work here. Because ultimately what I want to do is I want to combine these two radical expressions. So I had to break down this one a little bit, and I got this a simplification, and I have to break down this radical a bit more, and I get this simplification. And now I can replace these radicals with those simplified expressions, and now look what I get, guys. I get the same expression underneath the radicals. They're the same. So now I'm saying I got 4ABs rad 3ABs minus 8ABs rad 3ABs. So now that I have the same radical, I can leave the radical exactly the same, 3AB. And then what am I combining? I'm combining the coefficients, or I'm combining the expressions in front of the rad. So this will be equal to what? 4AB minus 8AB. And what is 4AB minus 8ABs? They reduce to negative 4ABs rad 3AB. And this is my final answer here. So we have to get comfortable with viewing radicals with different radicands. So the radicand is the expression underneath the radical. So if we have different expressions underneath the radical, I want to find a way to break them down so that I have radicals that are the same. And because I have radicals that are the same, I can now combine such expressions because they're the same kind. They're of the same radical. And there's a lot of letters here. So we have to get comfortable with viewing letters in such a way under radicals and being able to simplify those expressions. Okay, so let's try a few more of these. I got 6 multiplied by 75 minus 5 multiplied by 48 plus 2 multiplied by 32. So here we have 3 radicals. Again, they're all, I want to combine them. I'm subtracting and adding them, but they all have different radicals. So right now I can't do anything. These are all different. They're unlike. So the best thing I can do is try to see if it's possible to break them down in such a way that they have similar or the same like terms. So rad 75, I want to break that down. 48, I want to break that down. And rad 32, I want to break that down. So rad 75, what's the biggest perfect square that divides 75? Anybody out there?
Is it 25?
Yeah, of course. So 25, how many times does 25 go into 75? Like if you have 75 cents, how many quarters do you need?
3.
You need 3, right? So 25 times 3 is 75, and 25 is a perfect square. Well, that's great, because now I can break down 25. 3 I can't break down any further because rad 3 is simply rad 3. It's not a perfect square. But rad 25, square root of 25 is 5. So I got 5 rad 3. So rad 75 simplifies to 5 rad 3. Great. I'm good with this now. Now rad 48. What's the perfect square, the biggest one, that divides 48? So you have to know your perfect squares. 1, 4,
16.
16. That's right. So 16 multiplied by what gives me 48?
3.
3 again. Good. And so then I got 3. And this becomes the square root of 16 multiplied by rad 3. Square root of 16 is 4 rad 3. And great, I have simplified rad 48 to 4 rad 3. And then lastly, I have 32. What multiplies to 32? And where one of those numbers is the biggest perfect square that divides it. Again, go back to your perfect squares. What divides 32? And of course, I want to get the biggest one.
Is it 16?
It is 16 again. And 16 multiplied by what gives me 32?
Multiply by 2.
Multiply by 2. So then I get square root of 16 multiplied by square root of 2. I already know square root of 16 is 4. And I get 4 rad 2. So rad 32 is 4 rad 2. Rad 48 equals 4 rad 3. Rad 75 equals 5 rad 3. Now, I'm simplified each of these. Great. Now I go back to my original expression that I'm trying to evaluate, and I'm going to plug in those radicals with the simplified version. So instead of writing 6 rad 75, I'm going to write 6 multiplied parentheses 5 rad 3. So I'm replacing rad 75 with 5 rad 3 minus 5, and then rad 48 is really 4 rad 3 plus 4 rad 2. So all I did was I replaced rad 75 with 5 rad 3, rad 48 with 4 rad 3, and rad 32 with 4 rad 2. And then I'm going to perform multiplication here in each of these little pink segments. 6 times 5 is 30, rad 3. 5 times 4 is negative 20, rad 3. And I get 8 rad 2. So I got 30 rad 3 minus 20 rad 3 plus 8 rad 2. What I notice is that I only have 2 terms that are common, that have the same radical expression underneath. So rad 3 and rad 3 are the only things that can combine. You can't combine rad 3 with rad 2. They're completely different. So now to combine them, when you add or subtract, you leave the rad alone and you just combine the coefficients. So 30 minus 20 is 10. So I get 10 rad 3 as a final answer here, plus 8 rad 2. And that is my final answer. Okay, so I combined by adding and subtracting radicals, by breaking down each of those radicals into a simplified form, and then combining the like terms, or combining the radicals that are identical. I can do that. Okay. Okay, and so we've been doing a lot of radicals, but of course, square roots. Square roots aren't the only one, the only radicals that we should be able to simplify. We also have cube roots, fourth roots, right? So let's go into the world of cube roots for now. What if I get x, the cube root of 16 y to the fourth plus 4, the cube root of 54 x cubed y to the fourth minus xy the cube root of 250y. Okay, so obviously we're dealing with a different kind of radical. We're dealing with the cube root. Okay, and the radicals underneath the expressions underneath the radicals are all different, obviously. So I want to see, can I simplify? Can I break these down? Can I break down these radicals? So let's look at the cube root of 16y to the fourth. Now, we're not going to treat this the same thing as square roots. In square roots, we want to figure out what's the perfect square. In cube roots, we want to figure out what's the perfect cube that I can break this down with. So then what are the factors of 16 where one of them is a perfect cube? So we have to figure out what perfect cubes are. For example, 1 cubed is 1. 1 is a perfect cube. 3 cubed is 3 times 3 times 3, which is 27. 27 is a perfect cube. So what number divides 16 that is a perfect cube? Not perfect square, perfect cube. Anybody know what's a perfect cube that divides 16?
Is it 12?
So does 12 divide 16? So we want to know the factors of 16, and 12 is not one of them. And 12 is not a perfect cube either. So remember perfect cubes. What are the perfect cubes? 1 cubed, that's 1. 1 is a perfect cube. 2 cubed is what? 8. 3 cubed is what? 27. 4 cubed is what? 64. 5 cubed is what? 125. These numbers are the ones that you should know. 1, 8, 27, 64, 125. Sorry, this should be cubed. So what number divides 16 that's a perfect cube? It's not 12, it's 8. 8 times 2. 8 is a perfect cube. And now my question is, how do I break down y to the fourth where one of those factors is a perfect cube? Well, for this case, I can rewrite y to the fourth as y cubed times y, and y cubed is a perfect cube. Two is not a perfect cube, y is not a perfect cube. So then I'm going to do the same exact thing with the radicals, right? I'm going to put all the expressions that are perfect cubes on one. I can do that. I can separate them through multiplication. So I can do 8 times y cubed underneath the radical. And the remaining expression, 2y, I can just leave it in the other radical. And now, what's the cube root of 8? It's 2. What's the cube root of y cubed? It's y. And I have the cube root of 2y. So I was able to break down this first radical into a simplified version, 2y cube root of 2y. Now I have to do the same thing for the second guy. Take the square root of, not the square root, pardon me, the cube root of 54 x cubed y to the fourth. So 54, what perfect cube, the ones that you have here that you see, which one of those perfect cubes divides 54?
Is it
What's,
3 cubed times 2?
say that again?
3 cubed, which is 27 times
Correct.
2.
That's right. That's right. So 27 times 2, that equals 54. So 27 is a perfect cube. And then x cubed, the good thing about x cubed is it's already perfect cube. It's already, because it's cubed. It's already perfect cube. So I don't have to do anything for that. How about y to the fourth? Well, we just saw in the previous example, y to the fourth can be broken down as y cubed times y. So y cubed is also a perfect cube. And now I can replace or rewrite this as the cube root of 27 x cubed y cubed multiplied by the cube root of 2y. And now the cube root of 27 is 3 because 3 cubed is 27. So the cube root of 27 is 3. The cube root of x cubed is x. The cube root of y cubed is y. And I got the cube root of 2y. So the original expression that I had, the radical expression, the cube root of 54x cubed y to the fourth, was simplified into this new expression as 3xy cube root of 2y. So I simplify that as much as I could. And then finally, I'll do the last one. Now the last one here is the cube root of 250y. So again, the same question goes. The cube root of 250y. How can I break down 250? What number that I have here in the perfect cube list divides 250?
Is it 5 cubed, which is 125 times 2?
That's correct. So the cube root of 125 times 2, that gives me 250, right? 125 times 2 is 250. And this here is a perfect cube. And why do I care about the fact that it's a perfect cube? Well, now I can rewrite that as the cube root of 125 multiplied by the cube root of 2y. The 2y are not perfect cubes. Just leave it underneath the radical. But 125 is a perfect cube. And because it's a perfect cube, the cube root of 125 is 5. The cube root of 2y. So all I've done thus far is break down each radical individually. Now, once I've successfully done so, I can plug them back in to the expression. So the expression is what? X parentheses 3xy cube root of 2y minus, and then the next thing is what? Oh, plus 4, and then I do what? 3xy, the cube root of 2y minus xy, this becomes 5 cube root of 2y. Let me just see, everything is a-okay. Oh, pardon me, I wrote this incorrectly here. This should be this expression here. It's 2y. 2y cube root of 2y. Now I can combine by multiplication these terms here. And so I get 2xy cube root of 2y plus 12xy cube root of 2y minus 5xy cube root of 2y. Now look what I got. I got all these radicals are the same. The cube root of 2y, the cube root of 2y, and the cube root of 2y. Once I have that being the same, I can just leave that once and for all. And all I have to do now is combine all of the things, expressions in front of the same radical. So all I have to do is combine 2xy plus 12xy minus 5xy. The good thing is these are all common like terms as well. 2xy plus 12xy is 14xy minus 5xy is a total of 9xy cube root of 2y. A lot of breaking down of radicals. There's a lot of that happening. A lot. Okay, any questions about this? Simplifying radicals, adding, subtracting radicals, making them the same radicals so you can combine them. That's what we're into now. Okay. So that's simplifying radicals to add and subtract them. Now we're going to deal with multiplying them. Multiplying dividing radicals. So we talked about this a bit, about how we multiply radicals. As long as the kind of radical that it is the same, you can just multiply, you can multiply the expressions within the, you can multiply everything within the radicals. So you can't do this. So if this was, so I just want to make sure you guys understand the difference versus 3xy squared plus rad 27xy squared. These are two different things, okay? When I multiply radicals, I can play around with the inside of the radical. I can literally just do this. 3 multiplied by 27 multiplied by x squared multiplied by y to the fourth. I can do that. I can multiply the expression within. But I cannot do that here. I can't add them because these are different. They are different expressions underneath. The only thing I could do is see if I can break it down further, right? So I can break, for example, this is a perfect square. This is a perfect square. 27 can be rewritten as what? 9 times 3xy squared. So I can write this as the square root of 9y squared times the square root of 3x. Then I can write this as the square root of y squared times square root of 3x. And I get what? I get y rad 3x plus 3y rad 3x. So I get 4y rad 3x. So that's what happens when I add. So this is when I add these two radical expressions. But when I multiply, I don't get that. I just want to make sure you guys understand the difference. Please do not confuse the two. When you multiply, you can just multiply the things underneath. That's okay. And then I get what? I get the square root of 81 x squared y to the fourth. And all of these individually are perfect squares. Square root of 81, 9. Square root of x squared, x. Square root of y to the fourth, y squared. So you see, this is my answer when you multiply them. When you multiply these two radicals, I get 9xy squared. If I add to these two radicals, I get 4y rad 3x. Completely different. Two different things. So adding, you must have the same. Must have. So I'll make this a note. When adding, subtracting radicals, the expression must be the same. Sorry, the expression under the radical must be identical. When multiplying radicals, the expressions underneath radical can be multiplied to one another. Okay, so when you multiply, the radicals underneath could be different. When you add or subtract, they must be the same. So it's similar to like when you multiply fractions, you don't really care if the denominators are the same. But when you add or subtract fractions, then you really do care whether the denominators are the same. It's analogous to this. When you add radicals, you want to make sure that the radical underneath, the expression underneath the radical, are identical in order to combine. And if you multiply them, you don't really care whether they're or not they're the same. You can just combine them as long as they're underneath the radical. Okay, just make sure you understand the difference between those two operations. How else something like this? So let's see. I get the square root of 5a, and I'm multiplying that parentheses 20 rad 20a minus rad a. So what do we have to do here? We have to distribute. So I get 5a, rad 5a multiplied by rad 20a minus 5 rad 5a times rad a. What happens when you multiply? When you have two radicals and you're multiplying them, well, you can now multiply the two expressions underneath. 5a times 20a is 100a squared. 5a times a, rad a, is square root of 5a squared. And then 100, the square root of 100 is 10. And the square root of a squared is a. So that was a perfect square. Rad 5, however, is not a perfect square, but a squared in this one is. A squared is a perfect square. 5 is not a perfect square. So I have to leave rad 5 within the radical and take out the rad a squared. When I take the square root of a squared, I get a on the outside, and I get 5 being stuck in the radical. And this is the simplified expression for what I started with. Alrighty. So we're just extending our ability to multiply things. Now we have radicals all over. What if I get something like this? Rad x minus 4 squared. Now let me just tell you what you shouldn't do. And I think I've mentioned this before, but please do not do this. Rad 2, don't say that this is rad x minus 4 squared. That's not true. You cannot just take the 2's and square everything inside and say, yep, I did it. No. Remember, rad x minus 4 squared is the same thing as saying rad x minus 4 times rad x minus 4. That's what I get. That's what that means. So when I do that, I must do what? I must FOIL everything out. So rad x times rad x, what is rad x times rad x? Isn't the same thing as saying x to the 1/2 times x to the 1/2? And isn't this the same thing as saying x to the 1/2 plus 1/2? And isn't 1/2 plus 1/2 1? So rad x times rad x, so for now on, you should be able to know this now. This is a note. Rad x times rad x equals x. That's what it is. It's just x. So any radical, when you multiply by itself, you get back x. So example. Rad 7 times rad 7. What is that? Rad 49. But what is rad 49? 7. Rad 8 times rad 8. What is that? Rad 64. But what is rad 64? It's 8. Do you guys see that? It's rad 9. Rad times rad 9 is 9. Rad 101 times rad 101 is 101. It's because of the exponents. They add up to 1 when you add them. So rad x times rad x is just x. Rad x minus 4 is minus 4 rad x. Minus 4 times rad x is minus 4 rad x. Negative 4 minus 4 is plus 16. Then what do you have? Combine like terms. Get rid of the same rad x, rad x. So this becomes x minus 8 rad x plus 16. And that's going to be the simplified version of my expression. Rad x minus 4 squared is x minus 8 rad x plus 16. Okay, any questions about this? Let's see what else we got here. Yeah, how about if I get something like this? 4 minus 2 rad 7 multiplied by 1 plus 3 rad 7. The same idea. We want to distribute. So the first, outer, inner, last. The first two terms, when you multiply them, 4 times 1 is 4. The outer terms, 4 times 3 rad 7 is going to be 12 rad 7. That's the outer. So FOIL, F-O. And then the inner term is what? Negative 2 rad 7 times 1, which is just negative 2 rad 7. And then I do minus, because this is going to be a negative 2 rad 7 times 3 rad 7. So I just want to break that down a bit further. So this is the last, right? This is I and this is L. So of the last two terms, I get negative 2 rad 7 multiplied by 3 rad 7. So how do we do this? Well, we multiply the numbers that are on the outside. So negative 2, multiply that by 3. Because I could rearrange the order of multiplication. All these things are being multiplied to one another. I can write rad 7 times rad 7. What's negative 2 rad times 3? It's negative 6. What's rad 7 times rad 7? It's 7. Negative 6 times 7 is negative 42. So the last term here I get is negative 42. Then I combine like terms. 12 rad 7 minus 2 rad 7 is 10 rad 7. And then I combine like terms. 4 and negative 42, I get negative 38 plus 10 rad 7. Okay, so that's how we multiply. How we multiply radicals. As long as they're under the same radical, you can multiply them together, and things cancel out pretty nicely. So it's not as complicated as adding and subtracting. Analogous to how it's not adding and subtracting rational expressions is much harder than multiplying them, like we saw, right? Same thing here. When you add radical expressions or subtract them, it's more complicated because you have to break them down. But when you multiply, it's not as problematic. However, when you divide, there's a bit more involved with dividing, a bit more. So let's look at dividing radicals. So I think I mentioned the rule to you guys already before, but just to make sure, when you multiply, so I guess you can call it like the multiplication rule for radicals. If you have an nth root of something, multiply by the nth root of some other thing, that equals the nth root of the product. That's the rule. That doesn't work like that. Okay. So that's when you multiply. But when you divide, you need to do something different. So it's the nth root, for example, of something divided by the nth root of another thing. That is the same thing as if taking the nth root of a divided by b. And that's the rule here. That's the rule for dividing radicals. So example, if I take rad 5, a to the fourth, b to the seventh, c squared. If I divide this by the square root of a b cubed c, right? If I have such a thing, then what I could do is, based upon the rule, is I could take the square root of 5, a to the fourth, b to the seventh, c squared divided by a b cubed c. So the a's here become 3's, the c's here become 1's, and these here become 4's. So then I get this now. I get the square root, still the square root is there. I'm left with 5a cubed, b to the fourth, c. And now I want to see, can I break this down? Is it possible to break this down further? Well, 5, I can't break down any further. So 5 is stuck in the radical. C is stuck in the radical. But a cubed and b to the fourth, we've seen how we can break this up as products of perfect squares. So a cubed can be rewritten as a squared times a. B to the fourth can be rewritten as b squared. I should just write it. B squared times b squared. Isn't that b to the fourth? Oh, b to the fourth, I don't even have to do that. I could just say this is a perfect square. So this is a perfect square. Remember, perfect squares are expressions that have an even power. So the moment you have an even exponent, you're a perfect square because you can be divisible. That exponent can be divided by 2. So then I'm just gonna leave it as b to the fourth and then c. And so these are my perfect squares. So a squared is a perfect square and b to the fourth is a perfect square. So that means I can now rewrite this as the square root of a squared, b to the fourth, multiply that by 5ac. 5ac are all not perfect squares, so we leave that underneath the square root. But the square root of a squared is a. The square root of b to the fourth is b squared. So ab squared rad 5ac. And this is the result of division of the original 2 radicals that I had. Okay. So that's dividing. Now, so that's not the hard part, or not necessarily the interesting part. It's when we have to deal with what's called rationalizing the denominator. That's when things get a little bit more interesting. So you may have situations where the radical is underneath. So this is when the radical is in the denominator. So as an example, let's say I get 1 over rad 7. So what do I notice? Radical in denominator. I don't want a radical in my denominator. I want to rationalize it. So what does that entail? That entails me to multiply by some number. I have to multiply by a factor that makes denominator no longer irrational. If you notice, a radical is, this radical, rad 7, is irrational. Rad 7 is an unending decimal expansion with no no pattern to it. So then what we saw, remember what we saw in the note? What was the note? Rad x times rad x is x. So it makes sense that if I multiply rad 7 by rad 7, what do I get? Well, I get 7. And you see, 7 here is no longer radicalized. But whatever I multiply in the top of the bottom, I must multiply at the top as well, because I am multiplying by 1. This is really equal to 1. So when I multiply anything by 1, I leave it alone. I leave it the way, like, it doesn't do anything to it. So what I'm doing here is I'm not writing a new number. I'm just rewriting or expressing 1 over rad 7 as some other expression. So 1 divided by rad 7 can also be written as rad 7 over 7. That's why they're equal. So that's the idea. The idea is that you can multiply the top and the bottom by the very denominator. And when you do so, you get rid of that radical underneath the denominator. So let's see more of this. So for example, what happens if I get something like this? Look, rad 3 over 2x. What happens when I get this? Well, I'm going to use the fact that I can rewrite this as rad 3 over rad 2x. I can disassociate the radical as a fraction, right? So I have this fraction underneath a radical. I can separate them as a fraction of the numerator divided by the radical in the denominator. Same thing here. Now, what's the problem? I have a what? A radical or irrational expression in the denominator. I must make it non-irrational. I must make it rational. So what's the idea here? Multiply by exactly what the denominator is, which is 2x, rad 2x. And when I do that, what happens? Rad 2x times rad 2x is going to give me 2x. I already know this. And then what's rad 3 times rad 2x going to equal? Rad 6x. And I'm done. I have successfully rationalized the denominator. I can't divide the 2 and the 6. I can't, because 6 is underneath the radical and 2 is not. I can't do that. So, and the same thing goes for the x's here. I can't just cancel out the x's like that because of the square root. Okay. So what if I get now? What if I get something like this? Of course, we don't just get stuck with radicals. What if we get something like this? 3 over the cube root, no longer square root, but the cube root of 3x squared. Now, again, this is now, we have to visualize it or envision this using radicals. I mean, the cube root. When we deal with square roots, we're dealing with perfect squares. When we're dealing with cube roots, we're dealing with perfect cubes. So the reason why it works here to multiply by the radical is because the square root of something times the square root of another thing, that creates a perfect square underneath. So if you notice, rad 2x times rad 2x, what happens? I get rad 4x squared, which is a perfect square. This becomes 2x. Now, why do I make mention of this? Because now I have a cube root. So you would think, oh yeah, I'm gonna do the exact same thing that I did for radicals, for square roots. I'm just gonna multiply by the same thing, right? Underneath the radical. The problem is when you do this, you don't create perfect cubes, you create a perfect square, which is what we did when we had perfect squares. But we don't have a perfect square. So multiplying by this 3x squared will not cut it. It will not create a perfect cube. So I want to make this into a perfect cube. I want to create something in the denominator that's a perfect cube. So we have to be a bit more creative. We can't write 3x squared. I can't do that. What I have to do is try to figure out, hey, what do I multiply to 3? And what do I multiply to x cubed squared? What do I multiply to that so that I create a perfect cube? So 3 multiplied by what number gives me a perfect cube? So just think about what is perfect cube for 3. 3 cubed is 27. So it makes sense that I should get a 27 at the end. So 3 times what number gives me 27? I know you guys know this one. 3 times what number gives me 27? Nine. 3 times 9 is 27. And so I multiply by 9. And then x squared, I'm so close to making it a cube, right? I just want to make this into an x cubed so that it's a perfect cube. So then what do I need to multiply x squared to become an x cubed? I just multiply it by x. And now look what I have on the top. I got 3x cube root of 9x. Now look what I got here, guys. Perfect cubes. What's the cube root of 27? 3. What's the cube root of x cubed? X. And now look what nicely happens. 3, x, x. And what's my result? The cube root of 9x. So 3x divided by the cube root of 3x squared, the result of that is the cube root of 9x. Now just be mindful that this is the cube root, not the square root. So we care about making our denominators perfect cubes so that you can take the cube root of that perfect cube. Okay, so be mindful as to which radicals are being given to you to deal with. Okay, now the last thing for today is still along these lines of division, but now I'm going to be using what's called the conjugate. So we're going to be rationalizing the denominator using the conjugate. So I have this thing called the conjugate. So when does this happen? When do I use this idea of the conjugate? Well, I use it when I have a situation such as the following. What if I get this? 6 divided by 3 minus rad 5. So you see how these other ones, we just have a simple radical underneath, and that's it? Where sometimes we don't just have a simple radical underneath. Sometimes we have a number minus a radical or a number plus a radical. The problem is this radical in the denominator is irrational. I want to make the denominator rational. So what must I do? I must multiply by something. What is that something? That something is called the conjugate. And what is the conjugate? The conjugate is literally So these are called conjugates of one another. A conjugate is the same two numbers or terms, just opposite sign. So same terms, opposite sign. Same terms with opposite sign in between. That's it. That's the conjugate. Now, we should ask ourselves, why does this work? Well, remember when you multiply fractions, what do? You multiply across. So 3 minus rad 5, when I multiply this, I get 3 plus rad 5, right? Now, if you guys remember this is when you multiply two terms where one of them is a sum and the other one is a difference. That's related to the difference of perfect squares. If you guys don't remember that. 3 times 3 is what? 9. 3 times rad 5 is what? 3 rad 5. Negative rad 5 times 3 is negative 3 rad 5. And then negative times a negative times a positive is a negative. Rad 5 times rad 5 is 5. What happens with the inner terms? They cancel. So in reality, what I could have done is just said, hey, this is 3 squared minus rad 5 squared. And that's exactly what I get. I get 9 minus 5 equals 4. So when I do this operation by multiplying by the conjugate, what I get at the end is just a number, and a simple number at that, 4. So that's the point of multiplying by the conjugate. I get, instead of a radical underneath the denominator, I get just a nice whole number. And then I get this, 6 multiplied by 3 plus rad 5. I multiply, right? Now distribute, and I get 18 plus 6 rad 5 over 4. And at this point, the only thing I could try to do is to factor out the GCF in the numerator. And if I factor out the GCF, I get 2 multiplied by 9 plus 3. Well, the GCF was 6. So actually what I could have done, guys, in the beginning here, I could have just canceled out the common factor. So again, this is multiplication, so I can do this. Divide this by 2, divide this by 2, and I get 3. And then when I distribute the 3, I get 9 plus 3 rad 5 divided by 2. So this is as simple as it gets. You can also rewrite this as a sum of two different fractions. I can write this as 9 halves plus 3 rad 5 over 2 as well. I can also have done that as well. Okay, so now this is a new thing here where we multiply by the conjugate to rationalize my denominator. And again, this here, when you have a fraction, it's like saying you're dividing. It's like saying 6 divided by 3 minus rad 5. I'm saying, what is 6 when you divide it by 3 minus rad 5? Well, when you divide 6 by 3 minus rad 5, I get 9 plus 3 rad 5 over 2, or I get 9 halves plus 3 rad 5 over 2. Okay? So that's the last piece of it in terms of radicals here. Let's do one more of these. So what if I get like 1 minus rad 5 divided by 2 plus 3 rad 5? Now look at this. I got 1 minus rad 5, and I'm dividing that by 2 plus 3 rad 5. Just hook up my computer because it's gonna lose battery. Okay, so then I have to multiply by the what? By the conjugate. What is the conjugate? What's the conjugate of 2 plus 3 rad 5? Oh, whoops. It's not syncing. Hold on 1 sec. Let me get back to that. Okay, now we're good, right? So what's the conjugate of 2 plus 3 rad 5? It's 2 minus. Remember, it's the same terms, just different sign in between. So 2 plus 3 rad 5 becomes 2 minus 3 rad 5. And I do the same exact thing in the numerator. Now, what do I know, or what should I expect when I multiply 2 plus 3 rad 5? Multiply that by 2 minus 3 rad 5. Difference of perfect squares, right? So this should be what? 2 squared minus 3 rad 5 parentheses squared. This is what? 4 minus, what's 3 squared? That's 9. What's rad 5 squared? That's 5. So I get 9 times 5, which is 4 minus 45, which equals negative 41. So what I get here is a negative 41. That's what I get in the denominator. So I should write that down. This is the denominator. Now, what happens with the numerator? I get 1 minus rad 5 multiplied by 2 minus 3 rad 5. Here, I had to do the foiling because it doesn't cancel out the way the denominator does with the conjugate. So then I distribute, and I get 2 minus 3 rad 5 minus 2 rad 5 plus 3 times rad 5, which is 5. So I get 2, I combine like terms here. I get minus 5 rad 5 plus 15. Combine 15 with 2, and I get 17 minus 5 rad 5. That's what happens in the numerator. 17 minus 5 rad 5. And I can write it this way, or I can write it this way. 17 over negative 41 minus 5 rad 5 over negative 41. But the negatives here cancel, and I'm left with negative 1741 plus 5 rad 5 over 41. That's one way I can express my answer. Or I can just leave it like this here. Okay, so we're dealing with multiplying by the radical or the conjugate of radicals to make my denominator no longer irrational, but rational. Okay, and the conjugate, again, the conjugate is just the same terms. It's the same terms, it's just that the sign in between is the opposite of the original. So if this is a minus, like we saw here, if you got a minus sign, then the conjugate would just have a plus sign. If you have a plus sign, then the conjugate would just have a minus sign. That's really just it. That's how simple that is. And just be mindful when you multiply the denominators of the conjugates, it's the same thing as dealing with squaring both terms and subtracting them, difference of perfect squares. And when you multiply two radicals such as this, it's like foiling. You're really just performing foiling. And you're able to get the final radical expression. Okay, so we can stop here.